Good day. We are Group 6, composed of Redil Arreza and Jean Delima, here to present the topic of convective heat transfer coefficient for natural convection over surfaces and thin surfaces. For this presentation, we will be going over the introduction, the dimensionless numbers involved in solving problems for this lesson, then the discussion of the main topics. We will also be solving some example problems before summarizing the presentation. Natural convection, also known as free convection, is a mechanism of heat transfer where the fluid motion is generated solely by density differences in the fluid, which occur due to temperature gradients. This process does not rely on any external sources like a pump, fan, or suction device. In natural convection, buoyancy force is the critical driving force that sets the fluid in motion. It arises due to the combined effects of temperature differences and gravity. When a fluid is heated, it expands and becomes less dense, and due to the buoyancy force, it rises. This upward movement of the heated fluid creates a pressure differential between the heated fluid and the surrounding cooler fluid. Essentially, the buoyancy force tries to equalize the pressure difference caused by the density variations due to temperature changes. It's also important to note that the buoyancy force requires a gravity field, so in space, where there is no gravity, the buoyancy effects do not exist. The counterpart of natural convection is forced convection, which is a mechanism of heat transfer in which fluid motion is generated by an external source such as a pump, fan, or suction device. This externally induced fluid motion enhances the transfer of heat, allowing significant amounts of heat energy to be transported very efficiently. Forced convection differs from natural convection in the driving force, heat transfer rate, equipment requirement, and overall heat transfer coefficient. We will now go over the various dimensionless numbers that are necessary for solving problems involving natural convection, which include the Grashof number, Prandtl number, Rayleigh number, and Nusselt number. The Grashof number is a dimensionless number that approximates the ratio of the buoyancy to viscous forces acting on a fluid. It is analogous to the Reynolds number, which compares inertia to viscous forces, but specifically focuses on natural convection, where it provides the main criterion in determining whether the fluid flow is laminar or turbulent in natural convection. Larger Grashof number signifies stronger buoyancy forces compared to viscous forces, indicating dominant natural convection. This leads to a stronger fluid flow and higher heat transfer rates. Smaller Grashof number suggests weaker buoyancy forces relative to viscous forces, implying less significant natural convection. In such cases, forced convection might be necessary for effective heat transfer. The Prandtl number is a dimensionless number that measures the ratio of momentum diffusivity to thermal diffusivity in a fluid. In simpler terms, it indicates how efficiently a fluid can transfer heat through conduction compared to its momentum transfer through convection. Larger Prandtl number indicates dominant influence of viscosity over thermal diffusivity. This means heat transfer primarily occurs through convection, as the fluid's internal resistance to flow dominates heat diffusion. Examples include high viscosity fluids like honey or oil. Smaller Prandtl number suggests stronger influence of thermal diffusivity. In this case, heat transfer is more efficient through conduction, as heat diffuses quickly through the fluid. Examples include liquid metals like sodium or water. The Rayleigh number is a dimensionless number that describes the natural convection of a fluid by buoyancy and viscosity. It is the product of the Grashof number and the Prandtl number, which are related to the buoyant force and the thermal diffusivity of the fluid. This parameter helps predict when a fluid will transition from a static state to a convective flow, allowing for a deeper understanding of heat transfer behavior. A larger Rayleigh number implies stronger buoyancy forces relative to viscous forces, resulting in more vigorous natural convection and higher heat transfer rates. Smaller Rayleigh numbers suggest weaker buoyancy forces, with conduction playing a more significant role in heat transfer. The Nusselt number is a dimensionless number that measures the ratio of convective to conductive heat transfer at a boundary in a fluid. It essentially compares the actual heat transfer rate due to convection to what would occur purely through conduction across a stationary fluid layer. It indicates how effective the convection is compared to pure conduction. A larger Nusselt number indicates stronger convection, leading to more efficient heat transfer. This is desirable in applications like cooling electronics or heating buildings. Smaller Nusselt numbers suggest weaker convection, resulting in less efficient heat transfer. This might be undesirable but can be useful in situations where insulating properties are needed.
We now move forward to discuss natural convection over surfaces. Now, for natural convection heat transfer on a surface, this depends on the geometry of the surface as well as its orientation. It also depends on the variation of temperature on the surface and the thermophysical properties of the fluid involved. Heat transfer relations in natural convection are based on experimental studies. Of the many such correlations of varying complexity available in literature for any given geometry, the following table presents the most used empirical correlations for the average Nusselt number. First, we have the vertical plate that is constant in temperature, holding three Nusselt number relations of varying ranges. This is followed by an inclined plate which has similar Nusselt number relations to the previous. For a horizontal plate, there are three Nusselt number correlations applicable. This is dependent on whether the upper surface or the lower surface of the plate is heated, or if the lower surface and the upper surface of the plate is cooled. A for this geometry is the surface area and P is the perimeter. Following this is the vertical and horizontal cylinders and the sphere. An outer surface of a vertical cylinder can be treated as a vertical plate when the diameter of the cylinder is large enough that the curvature effects are negligible. This condition is satisfied if d is greater than or equal to 35L over GR sub L raised to 1/4. The average Nusselt number over the entire surface for an isothermal horizontal cylinder and for an isothermal sphere can be determined in the equation shown for each. Let us now discuss natural convection over thin surfaces. Thin surfaces of various shapes called heat sinks are often used in the cooling of electronic devices. Energy that is dissipated by these devices is transferred to the heat sinks by conduction and from the heat sinks to the ambient air by natural or forced convection, depending on the power dissipation requirements. In this case, the plates of a fin heat sink are approximated as isothermal. The fin structure of the heat sink plays a crucial role in enhancing heat transfer. By increasing the surface area exposed to the surrounding fluid, fins allow for more efficient heat dissipation through natural convection. The design of the heat sink, including factors like fin spacing, fin geometry, and material properties, is important for optimizing its performance in removing heat from electronic components. The relations for isothermal parallel plates and natural convection over fin surfaces for the Rayleigh and Nusselt numbers are as follows. The optimal fin spacing S can also be determined through the depicted equation. The rate of heat transfer by natural convection from the fins can be determined from the equation Q is equal to H times the quantity 2N LH times the quantity T sub S minus T sub infinity, where N is equal to W over S plus T. N is the number of fins on the heat sink, and T sub S is the surface temperature of the fins. Take note that all fluid properties are to be evaluated at the average temperature, that is T sub S plus T sub infinity all over 2.
Next, we will go over some example problems for natural convection over surfaces and fin surfaces using Microsoft Excel. For our first problem, Justin is planning to build a hotel situated in Baguio City, Benguet. He would like to install a central water heating system so that his guests can take a shower comfortably, with his desired temperature being 45 degrees Celsius. The pipe, however, is exposed to the city's cold weather at an average temperature of 15 degrees Celsius. What would be the heat loss due to natural convection, assuming that the pipe runs completely horizontally with a diameter of 4 centimeters and a total length of 30 meters? First, we need to identify the given. The temperature of the pipe surface is assumed to be equal to the desired temperature of Justin that will be flowing inside of the pipe, which is 45 degrees Celsius. Our T infinity, which is the ambient temperature, is 15 degrees Celsius. The given diameter of the pipe is 4 centimeters, which was converted to meters prior to solving. The given total horizontal length of the pipe is 30 meters. Next, we should identify the type of geometry of the object that we are working with in order to determine the correct formulas that we will be using. A pipe in this case is a horizontal cylinder. Finally, the dimensionless numbers that we are working with are evaluated at the bulk temperature. Therefore, we need to solve for T bulk to obtain the properties of air that we will be using to solve the problem. The bulk temperature is obtained by taking the average of the surface temperature and the ambient temperature, which in this case equals to 30 degrees Celsius. We can now start to solve the problem. The first dimensionless number that we can solve is the Rayleigh number, which is given by the first formula shown on the slide. The values that we need are gravitational acceleration, g, the reciprocal of the absolute bulk temperature, beta, the surface and ambient temperature, Ts and T infinity, respectively, the Prandtl number, and finally the kinematic viscosity, nu. Plugging in these values, we get a Rayleigh number of 1.75 times 10 to the negative 5. Next is the Nusselt number. Take note that this specific formula for the Nusselt number is only applicable for the horizontal cylinder geometry, which in this case is a pipe. Solving for the Nusselt number, we get a value of 9.0461. Now that we have the Nusselt number, we can solve for the convective heat transfer coefficient, which will be 5.8529 watts per square meter Kelvin. The total surface area of the pipe exposed to the surrounding air was calculated to be 3.7699 square meters. And finally, using the formula for the rate of heat transfer, the final value for the amount of heat lost throughout the pipe is 661.94 watts.
Let us now have a sample problem for natural convection over thin surfaces. Elijah, a young engineer, was tasked to design a passive heat sink for a new system on a chip developed by his company. Based on the size and power of the chip, he decided to have a 5 by 5 centimeter base. The fins are 1 millimeter thick and extend 3 centimeters from the base and are exposed to an ambient temperature of 25 degrees Celsius. How far apart should the fins be to provide the optimal heat transfer? What is the rate of heat transfer due to natural convection if the temperature at the base is 75 degrees Celsius? To start, we can list down the given from the problem and identify the table or tables necessary to solve what is required. In this problem, we are required to solve the optimal fin spacing S and the rate of heat loss Q. The table that will be needed is the properties of air at 1 atmospheric pressure. We first solve for the bulk temperature by taking the average value between the temperatures of the surface and the surrounding fluid. We then identify the properties of air using table A-15 at T bulk, which was computed to be 50 degrees Celsius. Having identified the thermal conductivity K, the kinematic viscosity nu, the Prandtl number, and the value for beta, we can now solve accordingly for the required. Using the relations for isothermal parallel plates and natural convection over fin surfaces that was presented earlier, the optimal fin spacing or distance should be 5.32 times 10 raised to the negative 3 meters, and the rate of heat transfer due to natural convection would be 7.98 watts. To summarize, natural convection is a method of heat transfer where fluid movement arises from variations in density caused by thermal gradients rather than external devices such as fans or pumps. The effectiveness of natural convection also relies significantly on the temperature fluctuations within the system. An integral aspect of natural convection is the dimensionless numbers involved, that is, the Grashof, Prandtl, Rayleigh, and the Nusselt numbers. The Grashof number describes the relationship between buoyancy and viscosity within the fluid. The Prandtl number describes the relationship between momentum and thermal diffusivities. The Rayleigh number is a product of both the Grashof and the Prandtl numbers, and the Nusselt number is the ratio of convective to conductive heat transfer at the boundary in a fluid. Solving natural convection problems hinges on the surface's geometry, orientation, temperature variation, fluids' thermophysical properties, etc. And in the design of heat sinks, factors such as fin geometry and material properties are important for optimizing its importance in removing heat from electronic components. This concludes our presentation on the convective heat transfer coefficient H for natural convection over surfaces and fin surfaces. Thank you all for listening.